Welcome to the second to last video of Chapter 11. In this video, we are going to learn how to find the areas of regular polygons. So we've already learned some formulas for parallelograms and trapezoids and kites. There isn't a formula, though, really for every single regular polygon. So if you look at the figures below, there isn't a set formula for a pentagon or a hexagon or a decagon. So we're going to learn how to approach all regular polygons. Before we jump into any notes, though, I do want to give you a heads up that this video can be kind of tough. It draws on some of our knowledge from first semester and the beginning of second semester and kind of brings it all together. And it's a few more steps than the other area problems that we've done. So stick with me, and I think that you all can get it. Before we even jump into any examples, we need to talk about what does it mean by a regular polygon. So you see all those pictures below. A regular polygon, if you remember, this is all the way back from Chapter 1, is equilateral. So all the sides are congruent. It's equiangular. So all the angles are congruent, and it's convex. Okay, so what I mean by convex is it doesn't fold in on itself. So figures that fold in on themselves, those are called concave. Before we jump into any area problems themselves, we need to look at finding some angle measures and also some vocab. So example number 1, in the diagram, ABCDE is a regular pentagon inscribed in circle F. Find each angle measure. Okay, so regular pentagon, all the sides are the same, all the angles are the same, and then you can see we drew a circle around the pentagon. This notation tells you that F is the center of the circle. So we're finding the angle measures below. Okay, starting with angle AFB. So this angle right here, angle AFB. Okay, if you can picture, there are actually 5 of those triangles. You see the red triangle? If we drew this, there's now 5 of those triangles. Okay, if we look at this part here in the middle of the circle, that's going to be equal to 360. So a whole circle is 360. We're only interested in one triangle, though, out of those 360 degrees. So if we take that 360 and divide by 5, it'll give us angle AFB, which in this case is 72 degrees. Next, we need angle AFG. So AFG would be this angle. Okay, you should intuitively be able to see that that's half of the black angle. So if I take that 72 we just found and divide by 2, we get 36 degrees. Okay, and then lastly, we want angle GAF. So GAF is this one right here. This is going to take a little redrawing. We have this 90, this is G, this is A, this is F. This is what we're looking for. Angle AFG that we just found is 36 degrees. Okay, so to find angle GAF, I can take 180, subtract 90, and then subtract 36. And when I do that, I get 54 degrees. Okay, being able to find these angles is very important. We're going to be using them when we calculate the area of these regular polygons. We have some quick vocab that we need to define before we're going to go on and actually calculate some of these areas. The first piece of vocab is the center. So we say that this is the center of the polygon. The center of the polygon is actually the center of the circle outside of the polygon. Okay, so in this case, that would be that point F. Point F is the center of the circle that is circumscribed, so drawn around the pentagon. The radius is any segment that connects the center to a vertex of the polygon. Okay, so our vertices are A, E, D, C, and B. So any segment that goes from F to one of those vertices is a radius. So we could say FA is a radius, FB is a radius, CF is a radius, etc. You should see that there are 5 that we can see right now, or 5 total even. Okay. The apothem is the height of the triangles that are in the polygon. Okay, so if we look back up at this example and we look at this red triangle, so we talked about how there's 5 triangles, each of this size. The apothem is the height of that triangle. So in this case, that would be FG. You should also be able to see that there's 5 apothems. Each triangle has its own height. Okay, and lastly, the last piece of vocab we need to know is the central angle. And this is the angle at the top of the triangle. Okay, so that would be the first angle that we found, that angle AFB. B, not G. Okay, that vocab may seem kind of random. It's not, though. We're going to be using that in the following examples when we're calculating areas. So we're going to look at an example together, example number 2, to help teach us the process of how we're finding the areas of these figures. Okay, so example 2, find the area of a regular hexagon with a side length of 3. Okay, perhaps the most important part of a problem like this is drawing a figure. If you draw the wrong figure, you're going to calculate the area incorrectly. So we have a hexagon, 6 sides. It's regular, all the sides are the same. So let's start with that. I'm going to draw it kind of big because we are going to be drawing inside of this figure. Doesn't look regular, but it is. All the sides are the same. And each side is 3. Okay, so here's the basic process. We don't know how to find the area of a hexagon, but we do know how to find the area of a triangle. So what we're going to do is we're going to break this figure up into triangles. Now, as you saw above, that pentagon had 5 triangles in it, 1 for each side. This hexagon then is going to have 6. So as you can see right now, I'm drawing in what are called the radii. If I drew a circle around this, that center would be the center of the circle. The radii go from the center to each vertex. Okay, so if I focus on this triangle right here, if I find that triangle right there, the area, I can multiply by 6 for the 6 triangles. Now, I don't have the height of the triangle. I'm going to need to figure that out. So here's what I have right now. I need the height. I know the entire base is 3. When I draw the height down, it gets split into 1.5 and 1.5. Now at this point, we should be asking ourselves, how do we find that height? You should recognize there's nothing we can do just yet. If it's a right triangle and we only know one side, we don't have any tools yet to find another side. So we're going to have to use some of those angles that we looked at in example 1. Now, is there any way for us to find this angle? Well, if there's 6 triangles, but we cut all of them in half, so this triangle right here is cut into 2, this triangle is cut into 2, etc. All 6 are. We have 12 triangles. We talked about the center has 360 degrees. So if we take that 360 and divide by 12, we get 30 degrees. So that's this angle up here. Now we're getting somewhere. Now we have a 30, 60, 90 triangle. So we have 30, 60, 90. And hopefully this ratio is right in our head since we just reviewed this. We get L, L root 3, and 2L. We have the side across from the 30 is 1.5, not 3, because remember the 3 got split in half. That tells us our L. So then we get 1.5 root 3 and 3. The height is across from the 60. So our height is 1.5 root 3. Okay, so now we're getting somewhere. Now we have the base and the height of the triangle, so we can find the area of one of those triangles. We get 1/2, the base of 1.5, the height of 1.5 root 3. Okay, now please be careful with this in your calculator. Don't put the root 3 in. It's possible for us to have an exact answer here, which is exactly what we would prefer, so please keep your answer exact. So in your calculator, you'll do 1.5 times 1.5. You'll get something, and then you'll divide by 2. And when you do, you get 1.125 root 3. Now, that's just the one triangle. That's not the entire hexagon. So now we have to ask ourselves, how many of those triangles exist in this hexagon? Well, let's look. The triangle we found was this one right here. We talked about up here that there are 12 of those triangles. Each side is split into 2. So what we'll do to find the area of the entire hexagon is take that one triangle and multiply by the 12 of them. Again, you're not multiplying the root 3 though. Take 1.125, multiply that by 12. And what you get is 13.5 root 3 meters squared. So that's the area of the entire hexagon. So to review before we go on to the next page, the general idea is you're splitting each side into 2 triangles, finding the area of that triangle, and then multiplying by how many sides you have. So let's flip to the next page. Okay, so our next one here. Number 3, calculate the area of the regular polygon below. Okay, so below we can see that we have a pentagon. Basic idea, you're breaking that figure up into a bunch of triangles. Like we said before, every side has a big triangle that we're cutting in half. So we have 10 triangles to begin with. In the triangle that's drawn, we have the height. We do not have the base though. So we're going to have to figure out how to find the base. Now, we need to think. Don't just jump into 30, 60, 90 because that might not apply here. If we look at that triangle, we know 2 sides. We're looking for the third side. So in this case, we can actually use Pythagorean theorem. We get b squared plus 6.5 squared equals 8 squared. I'm going to take 8 squared and subtract 6.5 squared, and when I do, I get b squared to be 21.75. If I take the square root of that, I end up with about 4.66. Now, we've talked about this before. You don't want to round in the middle of a problem. So that 4.66 is the base of each triangle. That's not what I want to use, though. That's a rounded value. That's not exact. So what I want to do is use that square root of 21.75. So the base of each triangle is either square root of 21.75 or 4.66. So in the last problem, what we did, after we found the base and height of the triangle, is we found the area of each triangle. So the area of one triangle is 1/2. The height is 6.5. The base is the square root of 21.75. If I plug that in my calculator, the area of each triangle is about 15.16. Now, if I want the area of the entire figure, I need to multiply by how many triangles there are. Now, this is where some students go wrong. Each side, remember, is split into 2 little triangles. So that 15.16 is one of the little triangles. Now, if there's 5 sides, each side has 2 of those triangles, I need to multiply by 10. So sometimes students multiply by 5. You need to multiply by the number of triangles there are, which is 10. So the final area then ends up being 151.57 units squared. Sometimes it will be possible to keep your answer exact, sometimes it will not. So in example 2, our answer is exact. Here, our answer is approximate. Try to keep your answer exact when you can. Before we move on to this next note, I just want to write down the general process of what we're doing each time. Okay, so first thing that we're doing is we're taking 360 and we're dividing by the number of triangles. That helps us find the central angle. So in example 3, 5 sides, there were 10 triangles. In example 2, 6 sides, we've divided by 12. Now sometimes that's not necessary. Like in example 3, it wasn't necessary to find the central angle. But generally, that's what you'll start with. And then what you'll do is you'll find the height and base of each triangle. You'll use that then to find the area of one triangle. And lastly, you'll multiply by the number of triangles. So in example 3, we didn't have to do step 1. We started with step 2. We had the height, we found the base of the triangle, then we found the area of one triangle, and then we multiplied by 10. So remember, each side is cut into 2 little triangles. Now, quick note, to find an apothem, a radius, or a side length, you have 3 possible methods. So by apothem, just remember that we mean height of the triangle. So to find the height of the triangle, there's 3 different methods depending on what information you have. You saw in example 2, we used special right triangles. So it could be 30, 60, 90, or 45, 45, 90. And then we saw in example 3, we used Pythagorean theorem. And then lastly, anytime you have a right triangle, you can also use trig. So depending on the problem, one of these will be the most appropriate method to use, and that's what you'll have to figure out. Okay, so now that we have that process and that note down, we're going to do 2 more examples together. Example 4, find the area of a square with a radius of 6. So for each of these, you're going to have to draw yourself a picture. If you draw the picture wrong, you're in trouble for the rest of the problem. Okay, so I have a square. You always want to find the center. We've talked about you're going to break this up into triangles. But we also talked about each side is going to have 2 triangles. So I'm going to drop this height right here. And then we know we have a radius of 6. 6 is this length right here. So in this case, I don't know the base or the height of those little triangles, so I'm going to need to find both. I can't use Pythagorean theorem because I only have one side. Maybe I'm going to use special right triangles, maybe I'm going to use trig. First thing I'm going to do is I'm going to take 360 and divide by the number of triangles we have. Now, 4 sides means there's 8 little triangles, which gives me a 45. That is the angle that goes up here. Okay, so now we see we have a 45, 45, 90 triangle. Sides are L, L, L root 2. The side across from the 90 is 6. Okay, so what this tells us is that 6 is equal to L root 2. We divide by root 2. So L is 6 over root 2. But then we've talked about before, you can't have a root in the denominator. So we multiply by root 2 and root 2, which gives us 6 root 2 over 2. 6 divided by 2 is 3 root 2. So that is our L. L happens to be both the base and the height of the triangle. So next step, I need to find the area of one triangle. So that's 1/2 the base of 3 root 2 times the height of 3 root 2. Now, in this case, we can keep our answers exact, so please do so. In your calculator, 1/2 times 3 times 3 is 4.5. And then root 2 times root 2 is 2. 4.5 times 2 is 9. Okay, so then if we're looking for the entire area of the whole square, we're going to take 9 multiplied by how many triangles there are. So again, pay attention here. 4 sides means that there are 8 triangles. So in this case, our area is 72 centimeters squared. Okay, what I want you to do right now is I want you to pause the video and draw a figure for example 5. So pause the video and try to draw yourself a figure for problem 5. Okay, so example 5, you should have drawn yourself a regular octagon with an apothem of 8. So remember regular, all the sides, all the angles congruent. Octagon has 8 sides. So it's not perfect, but hopefully you get the idea. Each side is broken up into 2 triangles. Okay, hopefully you remember what the apothem is. The apothem is the height of each triangle. So this is the apothem. Okay, so in the triangle, if we want to find the area of the triangle, all we are missing is the base. The hypotenuse on the triangle or the radius of the figure doesn't matter. It doesn't help us find the area of the triangle. So we need to find the base. We need to determine, do we need to use trig, special right triangles, or Pythagorean theorem? So we're going to take 360 and divide by how many triangles there are. 8 sides means that there are 16 triangles. So we get 22.5. So in this case, you should be using trig. Okay, so what I want you to do right now is I want you to finish this problem. Set up a trig ratio to find the base of the triangle. Find the area of the triangle then, and the area of the entire figure. Pause the video and come back when you are ready. Okay, let's see how you did. If we are remembering trig, 22.5, this is our opposite, this is our adjacent, so you should have used tangent. So tangent of 22.5 is b over 8. Put this over 1 and do cross products. The base then is 8 times the tangent of 22.5. Okay, so you get the base then to be about 3.31. Next, you should have found the area of the triangle, of one triangle, that is. It's 1/2 the base. Now remember, you want to use the exact value. You don't want to use 3.31. If you round in the middle of the problem, it's going to give us a bigger error at the end. So I'm going to use 8 times tangent of 22.5. So that's all the base, and the height is 8. So we get the area of one triangle to be about 13.25. That's one triangle. Remember to multiply by how many there are. In this case, there are 16 triangles, so we're going to multiply by 16. And when we do, we get the final area to be about 212.08 square inches. So hopefully that went well for you. If you made a mistake, hopefully this was able to show you where you went wrong. If you want to flip the page for the last 2 problems of this video, please. We are now on our last 2 problems in the video, the objective problem and a challenge problem. In this video, we learned how to calculate the area of regular polygons. We split each side into triangles, found the area of one triangle, and multiplied by how many there were. So I'm going to start you out with the objective problem, and then you are going to finish it on your own. First thing we want to do is split up into triangles. Remember that each side is split into 2 triangles. So that 20 now is split 10 and 10. You have the base of the triangle. In order to calculate the area, you're going to need the height as well. So I'm going to mark that as an H. Take 360 and divide by how many triangles there are to find that angle right there. And that'll tell you whether you can use special right triangles or Pythagorean theorem. Well, in this case, we can't use Pythagorean theorem. So special right triangles, or if you're going to have to use trig. What I want you to do right now is pause the video and finish this problem. Okay, hopefully this one went well for you. You should have gotten a final area of about 688.19 units squared. If you didn't, see if you can go back and find your mistake. Okay, so what I want us to end on right now is this challenge problem below. A regular hexagon with a side length of 30 millimeters has a square that shares one of its sides removed from the interior of the hexagon. Draw the figure and find the area. Okay, if we draw the figure wrong, we're going to get the rest of the problem wrong. So the figure is incredibly important here. We need to start with our hexagon. And then it says a square that shares one of the sides removed. So a square that shares one of the sides is cut out of the figure. So this is the area that we are looking at for. And then the side length is 30 millimeters. Okay, so how would we go about finding this? Well, if we want the final area, just a plan, is you're going to find the area of the entire hexagon and then subtract the area of the square. Okay, well, the area of the square is base times height. So 30 times 30 gives us 900. Now, the hardest thing to find is the area of that hexagon. So that's what we're going to do now. If we put our center in, each side, remember, is split into two triangles. If the entire side is 30, this is going to be 15, and this is going to be 15. Okay, so if I take 360 and divide by how many triangles there are, 6 sides, there's going to be 12 triangles. So I get 30 degrees. Remember that that's the angle up here. Okay, so now we can use this to find the height of the triangle. We can't use Pythagorean theorem, we only know one side. In this case, we're going to use special right triangles. So we get 30, 60, 90, which is L root 3, and 2L. The side across from the 30 is 15, so we have 15 root 3 and 30. The height is across from the 60, so this is the height. Okay, so next we need the area of one triangle, which is 1/2 the base of 15, the height of 15 root 3. Remember to keep this exact, so in your calculator you'll do 15 times 15 times 1/2, which is 112.5 root 3. Then you're going to multiply by the number of sides that there are, which in this case is 12. So the area of that hexagon ends up being 1,350 root 3. So our final area is 1,350 root 3 minus 900. That is exact. I know that that's not real pretty, so sometimes it's nice to give an approximate answer as well so you get an idea of how much that is. This is approximately 1,438.27 units squared. Oh, I guess not units. It's millimeters. Okay, when you come to class tomorrow, we will be checking to make sure that you have the objective problem finished. Please make sure you bring any questions that you have to class. See you tomorrow.